Okay, welcome all of you. A very good afternoon. The topic for today's discussion is low overhead system tracing with eBPF. My name is Akshay, and I work as a DevOps engineer at SAP Labs. So before we begin, I would just like to break down the topic into three different areas. First is system tracing. So with system tracing, what exactly it means is like you would want to trace various aspects of your system, be it CPU, memory, or different types of resources, which could cause problems with the functioning of your of any of the VMs or any systems that you might have deployed, be it production or some other machines. So system tracing, talking about in the kernel context, that is not something which is new, but there have been a lot of advancements from what it was some 30 years back and where we stand today. And when we talk about the tracing mechanisms, something which is expected out of these frameworks and systems is that they should be low overhead. So your system could already be under load, and you might be using these tools to understand the behavior of a system, what is going wrong with the applications, going wrong with the kernel, what it is doing. So these frameworks should not add up to the overhead which is already there on the systems, and derive some metrics with as low overhead as possible. And when we introduce eBPF in this context, basically things become programmable, they are production ready, secure. And the major areas where we gain advantages with these is networking, or the observability part, and the security. So this is a quote from Brendan's website. You do not need to know how to operate an X-ray machine, but if you happen to swallow a penny, it always helps to know that an X-ray machine can help you out. So same as with the tracing tools and eBPF in general. So you need not know how to write eBPF programs, but it always helps to know what the framework has to offer. And what are the capabilities that it already has, which you can put to use and basically observe and understand your system behaviors. So it always helps to understand where we are coming from. So initially, talking about the early 90s, we had the classic packet filtering model, wherein the administrators would want to understand what packets are coming in and going out of the system. And at that point, it was more of stack-based and filtering mechanisms, which had a lot of kernel to user space copies happening. So that was not very a good way to monitor your packets. So it has, basically when we are discussing about these things, it has its roots in the networking domain primarily, but then we'll see how things have changed as of today. So, but then around 93, there was a new addition to the Linux kernel. That was the BPF virtual machine, which was added by McCain and Jacobson. So this is an in-kernel virtual machine, which basically helped you with the same packet filtering model, but then this was pretty efficient. This won't copy all the packets from kernel to user space. Now the filtering would happen right inside the kernel, and only thing which the user space application is interested in would be copied to the user space side. So it was much more efficient, and this was a register-based system. For 20 more years, there was no major advancements in this, but then the underlying architecture, the CPUs and all were really growing. There was 64-bit register support, and then some new instruction sets that were added. So Alexei Startov basically introduced new things and enhancing this virtual machine to bring it to that point where it mimicked the native architectural performance. And that is when new eBPF maps were also added for in-kernel data structures. So you could also store the data that you are filtering right inside the kernel and not just pass it to the user space. And then talking about today, so till 2013, it was more of the networking side of things, but then they thought if the system is so performant, why not open it up to other use cases as well? And that is when the BPF system call was introduced, and which is sort of a multiplexer for various kind of operations that you would want to do inside this virtual machine. And recently, we had support added for U probes, K probes, USDD probes, and trace points. So mainly two different divisions, the kernel side of tracing and the user space side of tracing, the dynamic and static. So how many of you have used TCP dump? I'm pretty sure most of you would know about it. So the expression that we see on the screen right now, the host IP and the port, this is what gets converted to a BPF program at the backend. So TCP dump is pretty different from what it is today than what it was previously. So this gives the kernel capability to filter in a lot better way inside the kernel, and then only pass the packets that you would see on your user space side. Now, how BPF works. So in this diagram, basically, I would like to focus mainly on 2-3 different parts. One is the BPF system call that I talked about. It is what is helping you load the BPF programs into the kernel. And then you have something like BPF maps. Those are the data structures that are used by the BPF programs to store data inside the kernel. And then other components like verifier and BPF, this JIT compiler. So starting with BPF program, this is how you would start. You would write some particular C program, which is more of a handler for a particular event. Events here are the probes that I just talked about, the dynamic and static probes. So this probe handler would actually get called when something of interest happens in your system. So you could write these programs, and then using the LLVM or CLang compilation framework, this would actually get converted to a BPF bytecode, because we are talking about a virtual machine here. So we have an intermediate bytecode, which is then given to a JIT compiler that then converts it to the native machine code for execution. Once this is done, you would have the BPF bytecode available, which would then go to the verifier component. So you cannot just load any kernel and any C program to your kernel. It goes to the verifier component. This is where some basic level of checks are done, what this program is doing, what memory locations it is accessing, and what it is allowed to do. So there are many helper BPF functions available inside the kernel, and this is where all of this gets verified. So and then you have the once this verification is done, basically the program is given to the JIT compiler, which then converts it to the native machine code, and the program is loaded inside the kernel. At this point, it is registered to a hook. It tells the kernel that, okay, if anything happens that is of interest to me, just let me know. And then basically kernel passes some context. So you could be tracing a memory allocation in the kernel. So kernel gives some context to the BPF program at this point, that this is where the execution is currently, and you can do any manipulations or computation based on what is happening inside the kernel. BPF maps, trace pipes, and the perf buffers are basically the destinations that you could use to store your data or pass in some output or debugging information out of these programs. Now, talking about the C programs, not everybody, like I'm not a kernel developer, but things get critical or are difficult to manage when I have to program something in the kernel context. And that is when frameworks like BCC help us out. BCC is basically a BPF compiler collection, which has some ready-made tools and is a framework which helps you deal with BPF easily. So it has some front-end support for Python, Lua, and C++. Now you could pretty much write your programs in Python, which are converted to the appropriate BPF bytecode by the BCC system and then loaded inside the kernel. And it has support for CLang and LLVM compilation framework, which has a BPF backend subsystem, which is used to convert your program to BPF bytecode, and a libbcc loader kernel library. And once this program is loaded, then you can start handling your probes. This is a small example of what a BCC program could look like. So we're just importing the BPF package from the BPF class from the BCC package, and then just initialize the object out of it. In the text variable, what you see, this is the probe handler, which is executed by the kernel. So it has a syntax like kprobe __ sys clone. So whenever the clone system call is triggered on the machine, kernel will give control to this particular program at this point and passing in some basic context that it might need to decide what it needs to do. And the BPF trace print is a sort of a helper function, by using which you can just pass in some data to the trace pipes in your kernel. And then the trace print, what you see below, is just a blocking call on the trace pipe, what you have in the sysfs kernel debug events. The project is majorly being worked upon by the IOVisor company, which the repo name is there. The lead developer is Brendan Blanco. So with this screen, please don't get overwhelmed by the information that is here. So the idea to present this is that you can pretty much attach these programs to any single layer what you see on the screen right now. Starting from the applications, going down to device drivers, and the tools that you see on the screen, these are what is readily available in the BCC framework as of today. So if you want to trace what all files are being opened on your system, you could use something like OpenSnoop. Now this could help you with areas where some program is just trying to open a file and it just doesn't exist. So you could trace such behaviors with these tools. Exec-snoop might give you some idea about the short-lived processes, because with the normal tools that we use, we might not actually get to notice the short-lived programs which just come up, do something, and go off. Now this thing basically hooks into that kernel point where that program is exec and then gives you information. Off CPU time, as important it is to know how much time your process or application is spending on the CPU. It is also important to know what are the reasons or what the call stack look like when you actually went off the CPU. So that is also important to know. Something like profile gives you on CPU profiles, just sampling data after every few seconds, just tracing what is there on the CPU and gives you some information. This is what the output looks like. We have the biolatency tool, which just gives you what are the latencies that is which you observe on the block IO devices, and it just gives you a good histogram. So one thing which I would like to talk about here is the count column that you see. All of this data aggregation, computation, or any sort of filtering or discarding all the information in the kernel, all of this is happening inside the kernel. Previously, you would have passed all of this information to the user space. So that is a big improvement. When you're talking about CPU scheduling events, you're talking about the network details, this is something which is very efficient now. And something from the user space could just poll this data structure maybe every 5 seconds and get this 5, 15, or 20 integers. That's it. And all the other work is done by the user space program. What do you see the decoration part of it? Memory could give you examples of what bytes are allocated by a particular call stack, and it just keeps track of those memory allocations, what was not freed in that time till the time this program is actually running. Run queue latency could help you with things like what is the time for which most of the programs are waiting to get access to the CPU, and these things could help you with something like CPU saturation or CPU load. You could actually get to see that, okay, with these histograms, basically the main things to notice are with the outliers that are there just below the screen. That is something which you wouldn't want to drill further with other tools, like why it is happening. Profile, as I talked about, this gives you the on CPU call stack trace. This helps you know what is executing on the CPU. And going bottom up, this is the call sequence, basically all the ancestry that you see of the calls being made, all the functions, and you get to see both the kernel stack as well as the user stack. And the process ID 25279, that is the PID, and the number of events that were basically traced. Now, understanding all of this information in a live system often gets difficult. You have so much of data that you have to derive some analysis and intelligence out of the data, and that is where something like flamegraphs help you with. Flamegraphs is a tool that was built by Brendan Gregg from Netflix, and they're pretty much using it in production environments these days. So this helps you visualize the entire call stack that is there on the system and all the function calls that are happening. So this is a snapshot from one of the recent blog posts from Cloudflare, and using the flame graph, basically how they debugged some data center rolling upgrades that they were making, and eventually they could drill down to some misconfigurations in some property file that they had. So with these blocks that you see, the width basically defines what are the number of samples relatively that were noticed during the time frame during which this command was running. And then the call stack basically shows you the function call ancestry. Things are good, and then just to briefly touch down on a few things in context of containers. So talking about BPF and containers, there's not much that changes. So because container is nothing but a kind of a logical isolation that you have. We're talking about namespaces or C groups, some kind of resource limitation. So, but still they are resources, they are processes, and that are pretty much there on your host as well. So I'm sure you would be having an idea about the namespaces and the basic constructs that containers are having, but just to lay down some foundation here. So namespaces is something which restricts visibility. So as we had a discussion in the previous talk also, like depending on you're working with the PID namespace or the network namespace, container would see something which is not actually what exists on the host machine. So PID X on the inside the container could be a PID Y on the host machine. And the idea about discussing these things is that they don't really cause a problem when you're working with BPF, because it's just about mapping those PIDs on the host machine and inside the container. But then it is still a process that you are monitoring on the host machine. C groups is something which restricts usage or quota. So you could have quota defined for various resources like CPU, memory, or block I/O. And again, when a container is sort of CPU throttled or throttled on some other resource, you could notice some behavior that you could figure out from the flamegraphs. And then in assistance with the other tools like Docker stats or something, you would still derive information on what is going wrong. You could pretty much analyze these things directly from the host. The only thing that you might need to or take into consideration rather is the symbol file locations. Symbol file is something which just maps all the memory allocation addresses with what functions and variable names you're using inside your program. So these tools basically expect such mappings to exist in a particular location. For example, if you have used something like perf, it expects the perf-pid map file inside the temp directory, just to map these at runtime so that you can see the function names in the call stack in flamegraphs. Now you could use various different deployment methodologies when we talk about BCC in general. So you could have tools directly on the host, and which could just push in some events and then run inside the kernel and then observe the processes that are running inside the containers. One other mechanism could be or something which is more preferable, then rather than installing the tool set directly on the host, maybe you could just pull up a container which just shares or comes up in the privileged mode and then can monitor or give you a flame graph on demand. These are some things which I would also like to demo in the next slide. So let's start with a small demo. So here, basically, I plan to showcase three different aspects on what you could actually work with when you're working with BCC and BPF. So going with networking first, this is basically what you see on the screen right now. There's a dev stack setup that I have on my local machine. So and then two VMs running inside the same project, same network and same subnet. And I'll just run a trace on the ICMP packets that are flowing in, and then just initiate a ping request from one of the VMs. And we'll see what all interfaces the packet travels to. So if I just see, is it better now? Yeah, okay, sure. And then here we can see that the IP for this machine is 0.12, and the one below it is 0.13. So what I'll do is on the left side, I'll basically just initiate a packet tracer, and just before showing you the information, this is what I'm doing. So on the left hand side, this is the setup that exists when you're talking about VMs or network interfaces in context of OpenStack. So we have a virtual NIC which is just a representation of the tap device, and then we have a QBR bridge per VM, and which basically connects the tap device and the QVB. QVB and QVO are basically the VH pairs. which connect the QBR bridge and the integration bridge, and the traffic, if it is intended to for another VM on the same host, this is where it exits. And on the right-hand side, this is a BPF program that is working for tracing such requirements. So we are basically attaching our probes to these two events that are there in the kernel. In the networking category, we have net device queue and the net receive SKB entry. SKB is just the SKB buff. That is the basic data structure that kernel uses to transfer packets. And then we have a user space BPF program that just reads the data from the perf buffer that is there. So if I just initiate a ping from this VM to the one below, so what I see on the left-hand side is that the packet, it basically goes from the tap interface to QVB, QVO, the tap interface for the second VM, and then basically the source and destination addresses, you would see like after the first 4 entries, it just reverts. So then the packet starts from the 13 IP and then goes back to 12. So something like this, there's a very basic example, but just to give you an idea on what actually is possible with BPF. You can actually get down to these details, work something at the packet level, and then extract information out of it. And all of this is very secure, which is running inside the kernel. So and similarly, if you run something on the VM below, I could just see a similar packet traversal. Okay, so that was the networking part that I wanted to touch upon. So talking about the observability, this is basically a Postgres container that I have running on the machine. And this is a VirtualBox setup that I have on my machine. And basically what I'll do is I just want to trace the behavior of what this database is doing, what call stacks are there, and I'll trigger off CPU time flame graph from this. So on the left side of the screen, I'll just trigger a trace. So in the right side, you see that there's a BCC restified version of the BCC tooling. That is a container that has come up. And at this point, we also initiate a PG bench workload on the Postgres container just to have a real, just to mimic a real scenario. And then once that load is there, basically the BCC REST container kicks in and then traces the call stacks. So yeah, so sorry. So at this point, basically what we're doing is when this load is triggered, we just hit a REST endpoint on the BCC REST container that comes up. That is a privileged container that is running with access to all the host information that is there, and then using that, it basically generates a off CPU time frame graph. So this is something which was just created by this trace, and here we can actually analyze, like there's an interactive SVG visualization where you can just also search for things like where's my application, what the call stack looks like, and then you have the delimiters in gray where you actually leave the user space and then enter the kernel side of things. So you can actually go through these and drill down further into any of these call stacks and see what functions were actually executed and what the call stack looks like. And this would give you an idea on what actually happened when I was off scheduled the CPU at that time. So some blocking event or some wait on something. So, and then just giving a short demo on the security part. So I'll just do SSH into the same VM, and basically we'll see how I can so if I do the TTY, I can see that this is the PTS terminal that is there on this VM, and on the left hand side I can just trigger a snoop on this TTY device. So once that happens, basically any command that I run on this machine can be seen on the other program, that is the BPF probe that is running. Now this could again, this is a basic example, but you could pretty much extend it to have some secure mechanisms on what commands are being run by the systems inside your VMs and things like that. So those are three quick demos that I wanted to discuss, and so these are some frameworks that already exist as of today. So seccomp is something which limits the system calls or controls what a process is allowed to do and what not. So seccomp is also something that is used by Chrome browser to scope the execution or the commands that a plugin could actually do, or what it can or do or not allowed to do. And then something like Cilium basically is another framework which helps, which works in the container domain, and then helps with the networking, security, and the load balancing of the packets that flow inside a container host. And how it works is, we saw the various layers of the kernel diagram. So before the packet actually reaches the TCP/IP stack, it actually gets hold of that packet and does some analysis on where to route it or to maybe discard it. So those kind of decisions can actually be taken right inside the kernel. Weavescope is another project which basically gives you observability and what the connections look like in your containers applications, which container is talking to what. With IP tables have been there from long inside the kernel, and that is what helps you with enforcing some security rules. And previously it was IP filter that implementation that was in place. Now there's a discussion going on in the kernel community to actually come up with a BP filter implementation, which would use BPF programs to actually filter all the traffic on the system, and also to enable the hardware so that we can actually offload the filtering aspects to the network devices, and rather not bring them up in the operating system stack. Something like system tap is another framework which would help you write. It has its own DSL, using which you can basically write some probes, and then watch those or make some or do some actions based on those events. But the disadvantage with system tap was that it would basically come up with a kernel module and then load it inside the kernel. So that was not something which was secure enough, or could even break down your or cause a kernel panic. So there's some work going on with the front end part still remaining the same. You still write your system tap programs the similar way, but your backend implementation now gets converted to a BPF program and gets executed inside the kernel. And so that was all about the talk. Some references and some people to follow if you're interested in BPF. They're doing pretty much some good work in the BCC and the BPF community. Yeah. So that's all from my side. You can open up for questions. I'm sorry? Sure. Yeah. Any questions?
So you said that there's some discussions. Or could you elaborate on what the plans are for the IB tables to be replaced by BPF?
Yeah, so I don't have a lot of concrete details on what is going on, but the idea is like with IP tables, the like if the number of rows increase, right? So the way
I thought I read an article that said that they were going to be replaced. Is that still ongoing, or is that not finalized?
It's still ongoing, but the major blocker in bringing in those changes is that it should not break the existing production systems which are already using IP tables. So the front end still remains the same, how you define IP tables, so they don't want to change that. So there is no major configuration changes as such, but then just bringing in a kernel helper user space module, a user space application which can just convert those things and have a BPF program at the back end. But that is still under discussions.
Okay.
No concrete implementations as such.
Yeah, hi. I have two questions, both related. You talked about low threshold as one of the criteria for, utilizing eBPF filters.
The low overhead, you mean?
Yeah. That was one of the aspects.
Advantages, yes.
Now, when you have so many different hooks into the kernel, and you have these programs that are really written by somebody in user space, then turned into bytecode, then you have them running in the kernel. How is that aspect controlled? How do you maintain that low overhead? Because those filters could be doing a lot of things.
Right.
In each of those hooks.
So then basically what happens is like you have two things, sampling and tracing, right? So when it comes to events, that is more, for example, the CPU scheduling events, for example, now which is something there could be millions of events happening every millisecond, right? Sure. So in those cases, you would want to focus more on the sampling side, where you just trace the call stacks every few milliseconds maybe, not just have an ongoing a trace hook which just triggers your BPF program at every event occurrence. So that is how you should be controlling it.
But that's the responsibility of the person creating those hooks.
Yes, so kernel won't exactly take those decisions on your behalf, what you want to do. But again,
that could be intrusive. The point I'm trying to make is that if the users are not careful, there's no way that you could avoid that once those bytecode gets inserted into the kernel. You could basically extend the time that the kernel consumes in just running this code.
Right. So dealing with such things in production directly, maybe you would want to run those in a test system first, how it behaves. But the low overhead aspects also cover things like you can pretty much take decisions in kernel now, right?
And no, I got that part. But the overhead would be low only if you have that bytecode, is well contained in itself, right? But the overall cost in terms of getting that packet moving through the kernel increases because you're doing these additional things, right? And now when you have more hooks coming up, wouldn't the overall cost go up? And how do you contain that? That was kind of my point.
Right. So that actually depends on like how much tracing you're actually doing and what the event type is. You would definitely have to take that into consideration. Okay. But if I would compare it with tools like perf, maybe, right? So there, even if you're doing a similar tracing with perf and similar with BPF, the performance gain is still something which would help you out and delay the point where we would actually bring the system down.
Okay.
Yeah.
So the follow-up to that was I saw this different hooks that you talked about in the net. You had these hooks for SKB, receive, and other places. Right. Who controls these hooks? And is there if somebody needs additional hooks to be inserted into the kernel, is there like a forum to do that? I mean, who decides where these hooks exist in the kernel?
The hooks already exist in, okay, I'll maybe put it this way. There are hooks in the kernel already there, which the kernel developers might have placed some trace points in the kernel, that is static trace points. For somebody who might want to debug the kernel behavior in future, you could just hook into those trace points, right? And then you have something like dynamic kprobes, wherein you can just hook on to a dynamic kernel function, right? But that is not something which is stable enough because the APIs of the kernel could change, and trace point is something which is more stable. So And then the other side of things, like the user space side, you have some USDT probes, that is the statically defined trace points, which are existing or come up with various tools, like Postgres already has those. The Java, maybe I could show you a quick slide. Yeah. So if you look at the slide, basically all the environments, they already have these mechanisms in place for you, right? So you could just hook into these and trace any function at random in your application or any of these frameworks. So those mechanisms are there. You need not define a hook on your own. You just need to maybe have a quick understanding or check on Google, like what is the function that could help me out with such information, and just hook onto that. And the best part is kernel basically gives you context, gives you the arguments also on what this function received. So, and that is also secure. You are not dealing with the actual memory allocation where that data exists. BPF actually creates a copy of the data inside the BPF stack, and only then you can access or work on that. Does it answer your question? Yeah, great. Any other questions? I can see some of you sleeping. Sorry for that, if the presentation was boring. Or maybe lunch. Yeah. Okay then, thanks for your time. Have a good day.